An apple contains around 100 million individual cells and 10 to the power of 25 atoms, with each atom measuring just a nanometer across. The greatest number of items you could possibly fit inside an apple, measured in the tiniest cubic unit known as a Planck volume, is roughly 10 to the power of 102. Moving upward in scale, you could fit approximately 100 apples into the volume of an average human being, and about 10 to the power of 25 apples within the volume of Earth. About 10 to the power of 66 could fit inside the Milky Way galaxy, and around 10 to the power of 84 could fill the entire observable universe. This places both you and the apple at a crossroads, a meeting point of competing forces, interactions, and physical laws, a zone where the universe's opposing powers reach a delicate balance. The apple, measuring about 10 centimeters across, sits at a pivotal midpoint in the scale of the cosmos. It is roughly 35 orders of magnitude larger than the Planck length, the smallest meaningful distance, and about 27 orders of magnitude smaller than the observable horizon of the universe. In total, 62 orders of magnitude separate the very smallest from the very largest scales we know, a number that, in a sense, describes the entire cosmos and everything within it. Though it might appear arbitrary at first, the apple rests precisely halfway between these extremes, placing it at the center of the universal size spectrum. Understanding why it occupies this exact balance point may even help explain why the cosmos exists at all. At the close of the 19th century, physicist Max Planck was tackling what many considered one of the final puzzles in a mature field, mathematically describing the spectrum of light emitted by hot objects, like a metal rod pulled from a fire. Many brilliant minds had tried and failed. As a saying goes, there are two kinds of physicists, those who follow the rules and those who have physical constants named after them. Planck persisted, and after exhausting every conventional approach, introduced what he called a mathematical trick. He proposed that hot objects do not emit light in a smooth, continuous flow, but rather in discrete packets or quanta. To describe the smallest possible packet of light, he introduced a special number, a constant. With that, a revolution was ignited. By Planck's era, physicists were already familiar with constants. Some are human-defined, like the meter or the second. Others emerge naturally from the laws of physics, such as the speed of light or Newton's gravitational constant, values that simply exist without deeper explanation. But no constant before had described something so exceedingly tiny. The most precise measurements of the time could resolve objects a few microns in size, small enough to study bacteria. Planck's constant, however, pointed to a realm far, far smaller. 626 times 10 to the power of negative 34 joule-seconds defines where quantum effects dominate, where the certainties of our everyday world dissolve into probabilities and unpredictability. Planck combined his constant with three others: the speed of light, Newton's gravitational constant, and Boltzmann's constant, to create a set of reference points for the quantum realm, the Planck units. These include the Planck time, around 10 to the power of negative 44 seconds, the Planck energy, about 10 to the power of 9 joules, and the Planck length, roughly 10 to the power of negative 35 meters. These units mark the limits beyond which quantum chaos reigns and our current mathematics breaks down. Anything approaching these scales enters a domain where the familiar laws of physics no longer apply. Fortunately, we are unlikely to encounter these extremes anytime soon. The world's most powerful particle accelerator, the Large Hadron Collider, achieves collision energies of about 14 trillion electron volts. If a tennis ball carried that energy, it would glow as brightly as 100,000 Hiroshima explosions. 2 times 10 to the power of 20 electron volts, over 40 million times more powerful than collisions in the LHC. Yet the Planck energy is nearly 40 million times greater still. In 2020, a team of German scientists fired X-rays at a hydrogen molecule. The X-ray photon struck one electron, scattering it away, then ricocheted to hit a second electron. The resulting interference between the two electrons allowed researchers to measure the time it took for the photon to travel between them: 247 zeptosecons, the shortest time interval ever recorded. A zeptosecond is a trillionth of a billionth of a second. The Planck time is 23 orders of magnitude shorter than that. As for size, experiments trapping electrons show they are no larger than 10 to the power of negative 22 meters, the smallest direct measurement ever made. The Planck length is 1,000 billion times smaller. This Planck-scale world remains hidden from modern science, veiled even from our most advanced instruments. Yet through quantum field theory, we catch glimpses of what might occur at those unimaginably tiny scales. In the 1920s, Werner Heisenberg proposed a concept utterly foreign to our macroscopic experience: the uncertainty principle. It states that one cannot simultaneously know both the position and momentum of a particle with perfect precision. Measuring one property precisely inevitably blurs knowledge of the other. While Heisenberg originally framed this in terms of measurement disturbance, later work showed it to be a fundamental feature of nature, much like gravity or the fixed speed of light. The number governing this trade-off is none other than Planck's constant, the ultimate referee of the quantum domain. Heisenberg's principle implies that the quantum fields filling spacetime are never completely at rest. Even in a vacuum, these fields possess a baseline energy, a kind of irreducible vibration. At the Planck scale, these fluctuations cause spacetime itself to warp and churn beyond recognition. At human scales, spacetime resembles a smooth, unbroken sheet. Even with dips and ripples, it remains continuous. But at quantum levels, uncertainty allows particles to blink in and out of existence, and spacetime responds by twisting and flexing. This is the quantum foam, a seething, turbulent substrate of reality at distances around 10 to the power of negative 35 meters. Here, tiny whirls of spacetime and fleeting wormholes emerge and vanish. We lack the language to describe reality at this scale. Einstein's relativity demands smooth spacetime. Quantum theory says it is anything but. Many scientists doubt whether our current physics can ever make sense of the Planck realm. Consider a film. What we perceive as continuous motion is actually a series of still images shown rapidly. Our brain blends them into seamless movement. But if you could perceive each frame individually, the illusion would shatter. Is time itself quantized at the Planck scale? Does our smooth experience of time break down into discrete snapshots? What about space? We perceive motion as fluid, but could that be an illusion? Even our most precise instruments cannot probe near Planck scales. So the true nature of spacetime at that level remains a profound mystery. If we could shrink an apple down to the Planck scale, it would encounter forces beyond our understanding. The weakest known force, the weak nuclear force, operates over a range of about 10 to the power of negative 18 meters, far larger than the Planck length. At that minuscule size, the apple would experience all four fundamental forces: gravity, electromagnetism, and the strong and weak nuclear forces, merged into one unified interaction, similar to conditions in the earliest moments of the Big Bang. Under our current best guesses, such an apple would collapse into a singularity, a point of infinite density. However, in theories like loop quantum gravity, spacetime is discrete and pixelated at the Planck scale, preventing true singularities. Perhaps the apple would simply reach the smallest possible size and stop, experiencing energies and forces unknown to science, gazing directly into the quantum foam. Thankfully, our everyday apple is vastly larger, so we can still enjoy it as a snack. Between the Planck scale and the apple lies a crucial bridge: atoms. In 2025, scientists captured an image of a single hydrogen atom. They didn't photograph solid particles but mapped waves of probability, the likelihood of finding electrons in certain locations. What emerged was a pattern of rings and gaps, a portrait of quantum behavior. Atoms are about 100,000 times larger than electrons, and 10 to the power of 25 times larger than the Planck length. Even at this subatomic level, we are immensely far from the deepest structures of reality. Why are atoms the size they are? Why are all atoms of a given element identical across the cosmos? The early quantum model proposed by Niels Bohr depicted electrons orbiting a nucleus in fixed quantized paths, much like planets around the Sun, but with restricted options. For hydrogen, the closest an electron can approach the nucleus is defined by the Bohr radius, roughly 10 to the power of 24 Planck lengths. The nucleus itself is far smaller, about 10 to the power of 20 Planck lengths across, meaning atoms are overwhelmingly empty space. Their size is determined by the balance between electromagnetic attraction and the quantum rules that govern electron waves. Erwin Schrödinger later refined this picture by describing electrons as matter waves. An electron's wave must fit neatly around the nucleus, like a vibrating string fixed at both ends. Only certain wavelengths and thus certain orbits are allowed. The 2025 experiment visualized these probability waves, not solid particles. Where the wave peaks, the electron is likely to be found. Where it dips, the electron is unlikely to appear. This wave nature becomes increasingly significant as we approach Planck scales. Even large molecules containing thousands of atoms have shown measurable wave-like behavior. Deep within the atomic nucleus, another force dominates. Protons and neutrons are packed incredibly close, experiencing immense electromagnetic repulsion. Yet nuclei don't fly apart. In 1934, Hideki Yukawa proposed a new force, the strong nuclear force, mediated by particles that bind protons and neutrons together. Overcoming this force requires energy, which is why nuclear reactions release such tremendous power. Harnessing the binding energy from all atoms in a simple sandwich would yield an explosion comparable to a multi-megaton nuclear warhead. But the story goes deeper. Protons and neutrons are not fundamental, they consist of quarks. In 1995, experiments at Fermilab confirmed the existence of the top quark, the heaviest of the 6 quark types. Quarks are bound by the strong force carried by gluons. This force is so powerful that quarks are never found alone. Trying to separate them only creates new particles. The size of an atomic nucleus is set by the balance between the strong force, which binds protons and neutrons at close range, and electromagnetic repulsion, which pushes them apart. The heaviest known elements, like oganesson with 118 protons, stretch this balance to its limit. So why do quarks and electrons have their specific masses? We still don't know. It remains one of physics' great mysteries. From the quantum chaos of the Planck scale emerge particles and forces that, through precise balances, build atoms. And from atoms, through further complexity, life arises. Life spans an enormous size range, from bacteria measuring a few hundred nanometers to fungal colonies covering square miles and weighing tens of thousands of tons. The leap from a bacterium to the largest fungus is greater than the leap from an atom to a bacterium. At the scale of life, physics exhibits emergence, complex behaviors arising from simple rules. Conway's game of life demonstrates how basic rules can generate astonishing complexity, even to the point of simulating a computer. In nature, simple rules guide bird flocks, ant colonies, and the wetness of water, properties that cannot be predicted from individual components alone. Billions of years ago, molecules made the leap from non-living to living, an emergent transition that still eludes full explanation. A single bacterium is arguably the most complex structure in the universe, processing information and energy across many orders of magnitude. Human beings exist at this scale, governed largely by electromagnetism. This force binds atoms into molecules, molecules into compounds, and compounds into tissues. It drives nerve signals, heartbeats, and touch. Electromagnetism also sets limits on life size. The smallest organisms must be complex enough to perform life functions, requiring a minimal number of atoms. The largest creatures are limited by how quickly nerve signals can travel and how effectively they can dissipate heat. The largest possible land animal is estimated around 120 tons, just slightly larger than the massive dinosaur Maximo. Centuries ago, units of measurement were based on human experience: a foot, an acre. The French Revolution introduced the meter, originally defined as 1/10,000,000th of the distance from the North Pole to the equator. In 1983, it was redefined using the speed of light, a fundamental constant. This meter-scale world, from nanometers to tens of meters, encompasses all of life. Within an apple's cells, biochemical machinery operates via electromagnetic and nuclear forces. Cells resemble bustling cities with protective membranes, a nucleus housing DNA, proteins acting as repair crews, and mitochondria or chloroplasts providing power. But one force remains dominant at much larger scales: gravity. Stars exist where gravity's inward crush balances the outward pressure from nuclear fusion. Our Sun, containing 99% of the solar system's mass, is powered by fusion in its core, converting hydrogen into helium and releasing neutrinos. In the late 1990s, the Sudbury Neutrino Observatory solved a solar mystery by showing that neutrinos change flavor during their journey, confirming that fusion alone powers the Sun. Every minute, the Sun fuses an Earth's worth of hydrogen, releasing more energy each second than humanity uses in 100,000 years. Stars come in a range of sizes. The smallest, red dwarfs, can be as light as 88 times Jupiter's mass. Any smaller in fusion cannot ignite. The largest known star, R136 Aeon, holds about 300 solar masses and shines millions of times brighter than our Sun. Above this limit, radiation pressure would tear a star apart. In the early universe, the first stars may have been 10,000 times more massive than the Sun. Larger than individual stars are molecular clouds, vast assemblies of gas and dust that give birth to stars, and the remnant stars leave behind, like neutron stars and black holes. From the Planck scale to atoms, from atoms to life, and from life to stars, the universe builds complexity through balances between competing forces. Each scale reveals new layers of emergence, where simple rules give rise to astonishing phenomena. The apple and we ourselves sit at a nexus in this grand hierarchy, a testament to the intricate and balanced architecture of reality. If you enjoyed this journey through the scales of the universe, please support the channel by subscribing, liking this video, and sharing it with others curious about the cosmos. Your engagement helps bring more content like this to light. Thank you for watching his video and sharing it with others curious about the cosmos. Your engagement helps bring more content like this to light. Thank you for watching.